Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And you might be wondering, why are we talking about diffusion? Diffusion is easy. Not really, it's more complicated than you think, just in terms of going from higher concentration to lower concentration based on gas molecules in terms of when it is released. But in this particular video, we're going to dive into how you're going to connect diffusion to other properties of matter in terms of the mean speed of matter. You're also going to explore more about specific outcomes in terms of the free path based on the mean, and also looking at how this is going to be rightfully important in terms of temperature and pressure, and also the size of that particular particle in that particular space. So this particular video here, we're going to dive into our fundamental path, which involves transport properties of perfect gas. And you're wondering, what is this particular perfect gas? We know perfect gas is linked really well to what we know about ideal gases. And ideal gases are mainly gases that collides elastically without any form of reactions that may come up. Based on the transport properties, there are many interesting transport properties that we know of. One is involving looking at matter and how matter is transferred, and also in terms of looking at how we can connect this to another type of property, which is energy. And so our final one here is linear momentum. And so in this particular video here, we're going to be focusing on matter and introduce flux. And you might be wondering, what is flux? Flux is pretty much how energy or any form of quantity is mobile, or the rate of migration happens based on the property that you're measuring. And so this property of target in this case is going to be focusing on matter. And so in this particular video here, we're going to explore the migration or the rate of migration of that property at a specific area at a specific time interval. And this particular rate is going to be explored based on matter. And so we know that matter is anything that has weight and occupies a specific space. That is the general definition of matter. But in here, based on what we know about matter flux, we need to know a couple of interesting background involving this. One is this: when matter flows from one point to another in terms of diffusion, this is actually based on the number of many particles that are in a particular per square meter per second. And so based on this idea, we can then apply this idea to a space system, where in here we have a specific cuboid, and this cuboid contains a particle. And this particles, of course, there are many particles, and these many particles, they are at a high concentration in this region here. And so when they are high in terms of the concentration here, we know that this particular system is placed along the z-axis. And so placing this along the z-axis is going to be plotted alongside that of the number of particles, because we are looking at the migration of number of molecules at a particular area, which is here, at a particular time. So in this particular part, what we notice is that we are moving from high concentration here to some kind of a low concentration. And so as a result of that, we have our graph which shows a downhill slope that is not constant and it's changing. And so what we see is that if you plot this and we look at our observation shows that there is an increase in our flux, and our flux here, take note, is represented as J. So in this part here, we're going to be measuring our J for matter, which is the same thing as our matter flux. So our J for our matter is increasing, which we're going to assume to be, in this case, greater than 0. And so as the matter flux increases, we notice that, hey, these slopes here is having a negative value, but the negative values are decreasing. But you notice that they are all less than 0 based on the slope. Therefore, our change in the number of particles is less than the specific value, which is 0. Therefore, our derivative of our number of particles is less than 0, looking at this particular curve right there and taking the specific slopes. So, noticing this, we know that based on our analysis, we can lead to the conclusion that first, our specific flux, which is indicated here, is, take note, increasing as our specific concentration, take note, based on the rate derivative concentration is increasing, because we are going from larger values of negative numbers to smaller values of negative numbers based on the slope. And so this shows that there is a direct relationship between the matter flux and the first derivative of the specific number of particles with respect to our z-axis. And so as a result of that, we can lead to our introduction of our constant, which is represented as a particular value, which we're going to talk about very soon. Take note that since we have that condition where we have positive matter flux, but it is equal to negative derivative of our number of particles with respect to our specific z-axis, we need to determine our constant. And our constant here is indeed going to be a negative value, because negative here times negative gives us a positive value for our flux. As long as our value for our constant is negative, we'll always have our derivative of our number of particles to be negative, which means that we're going to end up with a positive j value. So in this part, we can then conclude that our constant will be expressed as d, and d is equal to the diffusion constant, and the diffusion constant is also expressed as the diffusion coefficient. And so our diffusion coefficient is always going to be negative, always negative. So our diffusion coefficient, take note that it is measured in meters squared per second, and for our matter flux, which is represented as J, the unit is measured in terms of the number of particles divided by the specific area squared, which is in meters squared, times the time, which is in seconds. So in this part here, once we have our diffusion coefficient established, how are we going to relate this coefficient to various interesting variables that we did on our previous videos? What we notice is that the diffusion coefficient is equal to 1/3 of our mean free path multiplied by our specific mean speed. So in this part, we can assume that, hey, since our mean free path is derived from our previous videos as mean speed by 1 over the specific collision frequency, and this is also equal to our Boltzmann constant multiplied by the temperature or divided by our pressure and the specific cross section of our specific particle, and this is multiplied by a square root of 2. On the other side, we know that our C is equal to, in this case, C bar is equal to the mean speed, and the mean speed is equal to. So these two relationships are key to be able to determine the diffusion constant, which is represented as D. And so if you're given a question that gives you the temperature, pressure, the cross section of that particle, you can assured determine the diffusion constant of that specific particle at that specific temperature and pressure. Now you're wondering, how will this pressure and temperature relate really well to the diffusion coefficient? Because that is what you are waiting for. And indeed, that is where we have various descriptions that highlights what we know about the diffusion coefficient and describing diffusion based on those interesting parameters. One is this. We know that the mean free path decreases as the pressure increases. So based on this relationship here, we have our mean free path is indirectly proportional to our pressure. Therefore, our specific collision frequency is inversely proportional to the mean free path. So once we have this established, we know that relating this to our D, which we have right here, which is determined to be the diffusion coefficient, we know that the diffusion coefficient is therefore decreasing as the pressure increases. So as a result of that, we can arrive at our conclusion that, hey, in this case, gas molecules will actually diffuse more slowly in this particular part when you increase the pressure. So that is one particular assumption to keep in mind in terms of this relationship right here, relating our mean free path with our pressure and then connecting it overall to the diffusion. Secondly, we have the other one which shows our relationship with the specific mean speed and the temperature, where in this case we know that as the mean speed increases, we have our increase in temperature. Therefore, our mean speed is directly proportional to our temperature, and as a result, we can then lead to the conclusion that connecting this to our specific diffusion coefficient, this increases at increasing temperature. Therefore, a hot molecule will diffuse faster than that of cool molecules. So this is quite interesting to see, and how we are able to connect our specific speed, mean speed, with that of temperature and overall to the diffusion. And finally here we have our specific expression that connects our specific mean free path, which increases with that of our cross-sectional area of that particle, which shows that the cross-sectional area of our molecule will also, in this case, decrease. So as a result of that, our diffusion will only increase for smaller particles compared to that of larger particles. So that is how this actually plays out in terms of highlighting what diffusion coefficient actually does in terms of connecting it to not only the cross-section of our molecules, but also the temperature and also the pressure. So that is how this actually plays out. So that's about it for this particular video. Hope you're able to understand this particular connection between diffusion, the matter flux, and also various outcomes like the mean free path and that of the mean speed in collaboration with the pressure and the temperature of a particular molecule in terms of its size. On our next video, we're going to apply an example to this particular formula that we actually showed here, and I hope you actually find this informative. Please hit the comment down below. Let me hear your thoughts about this, but that way I can talk to you all soon. Stay smart as always and believe in yourselves.